Okay, there are a few sorting algorithms that you need to have met for this course, but you don't necessarily need to learn. So you don't need to learn these off by heart, but you do need to have met them because you could be asked to execute them via a flowchart or pseudocode or written English, and you may be asked to name the algorithm that you've used. So there's 5 that we're going to look at. So there's bubble sort, one called Shuttle Sort, Selection and Interchange, Insertion sort, and Quicksort. So I'm going to cover all of those very quickly with this simple list of 5 elements. So the bubble sort, it's called the bubble sort because what tends to happen is the small numbers tend to float to the top. And what we do is we look at the bottom pair of numbers and we decide, do they need to swap? All sorting algorithms will sort from smallest to biggest, but a small modification will allow you to sort from biggest to smallest if you want to, or you can even sort qualitative data algebraically. We're going to check first the bottom 2 numbers and decide if they need to swap, and they do because we want the smallest on top. Everything else remains in position. So it's just the 2 and the 6 are swap places. And then we check the next 2, and we can see that actually, yes, they need to change places again, so 2 and 7 this time. And I'm just putting little arrows here just to emphasise any changes that are made. Then we look at the next 2, and we know that these 2 actually, yes, need to swap as well. And this one here, again, they swap positions. 2 goes up there and the 5 goes down there. Once you've managed to go from the bottom of this to the top, that's the end of what we call the first pass. And at the end of a pass, on the bubble sort algorithm, we can guarantee that the top number is the smallest, because the smallest number would have floated to the top, which is why it's called a bubble sort. It tends to, the smaller numbers tend to work their way up. And then we repeat the process again, but we stop when we get to here, because we already know the top number is the smallest, so we just repeat the process for the bottom 4 numbers. And then that'll be the second pass. And then we repeat the process for the bottom 3 numbers, and that'll be the third pass, and so on. So look at these 2 numbers, do they need to swap? Yes, they do. So 2, 5, 4, 6, 7. Look at the next 2 numbers, do they need to swap? No. 2, 5, 4, 6, 7. I'm just going to put little horizontal lines there, just to emphasise nothing is swapped. And then 2, 4, 5, 6, 7. We can see that those 2 have swapped. And that's the end of the second pass. Okay, I don't need to do the top 2 because I already know the top one is the smallest. Now we can see that this list is already now in numerical order. But the problem is the computer doesn't know that. The computer's just been comparing 2 numbers as it's gone along, and it cannot tell that this is now sorted. So the algorithm would actually just continue, and it would repeat back to the bottom. It would check to see if these 2 needed to swap, and we can see that they don't. Then it would see if the next 2 needed to swap, and they don't. And that's the third pass. And then finally, it would have to check the bottom 2. And again, we would come to the conclusion that nothing swaps. And that ends the algorithm. All in all, if you fully execute this algorithm, you are looking at 10 comparisons for a list of 5 numbers. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we've had 10 comparisons. And in this case, there were 6 swaps. And in general, if you have n numbers, in this case there were 5, then you are looking at the number of comparisons that are going to be made is equal to the n-1th triangle number. The n-1th triangle number. So in this case, there were 5 elements in the list, so we had the 4th triangle number, which is 10. Now, the n-1th triangle number is n times n minus 1 over 2. And you can check that in this case, 5 times 4 is 20, divided by 2 is 10. And this implies that this algorithm has quadratic complexity. Because the number of comparisons that one needs to make to execute this algorithm is proportional to n squared. Okay, that's the highest power of n. Second algorithm, Shuttle Sort. This one is similar to the bubble sort, except rather than sorting a number in position each time, it looks at the list and says, okay, well, I'm going to sort those two out. And then, in this case, it would swap them over, and everything else remains the same. And that's the end of the first pass. When we did the bubble sort, each pass gave another number into the correct position. So after the first pass, the 2 was guaranteed to be in position. After the second pass, the 4 was guaranteed to be in position. After the third pass, the 5, and so on. In the Shuttle Sort, however, at the end of the first pass, we can guarantee that the first 2 numbers are sorted. At the end of the second pass, we can guarantee that the first 3 numbers are sorted, and so on. So here, we now check the next 2. So we get 4, 5, 7, 6, 2, because there's no change. And 4, 5, 7, 6, 2. So it works its way up. So you did the first 2, then you did the second and third, then you do the first 2 again. And now you would do the fourth and fifth, sorry, the third and fourth. This is the second pass, by the way. And we can see that this, they do need to swap. So we get a 4, 5, 6, 7, 2. 4, 5, 6, 7, 2. 4, 5, 6, 7, 2. Okay, because no swaps need to take place there, and no swaps need to take place there. And that is the end of the third pass. And we can see that at the end of the third pass, the top 4 numbers are guaranteed to be in order. And what you'll find is that the shuttle sort is called the shuttle sort because each pass it takes the next number in the list and shuttles it up into position. And then it'll go to the next number and shuttle up into position, and the next number. And the list of sorted numbers gets bigger and bigger each time. So for the final pass then, we're going to swap the 2 and the 7. Then we swap the 2 and the 6. Then we swap the 2 and the 5. And then we swap the 2 and the 4. And that is the fourth and final pass finished. And we can see again that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 comparisons, just as there were with the bubble. And again, if you execute this algorithm in its entirety, then n numbers implies n times n minus 1 over 2 comparisons. So again, it's quadratic in its complexity. I keep saying in its entirety because this algorithm is fairly easy to program such that if you don't make a swap, then you don't have to continue with the pass. So for example here, because there was no swap between the 5 and the 7, you wouldn't need to do that comparison because you already know that they are in order. Same thing here. So you swap those, then you have to check these. If they don't swap, then you don't need to do that. So you could just move on to the next pass at this point. So you can actually increase the efficiency of the algorithm slightly. Selection and interchange. What we do is, for each one in the list, we look down the list and decide which one needs to go there. So at the top of the list, we want the smallest number, so we look down the whole list and we choose the smallest. So in this case, it's 2, and we swap it with what is there. So the 2 and the 5 swap places. Then we look down the list again, so we ignore that, and we choose what's the smallest number here, and we put it in the position where the 4 is. we already see that the 4 is already in position. That just remains where it is, no swaps. Then we look for the biggest number of the remaining 3, and that's a 5. So the smallest number of the remaining 3, that's a 5. So 2, 4, 5, 6 and 7. So those 2 have swap positions. And then finally we look for the 6 to go in the position where the 6 is. And then by default that means the biggest number must be at the bottom. So the section interchange is much quicker to write out and is more intuitive for a human, but it's harder to program. Okay, because you continually have to look down the whole list and find the smallest, and then make it a swap. And your list just gets one smaller, and then you repeat the process. That's the selection and interchange. It also has quadratic complexity, but you don't need the level of detail that you need to know for the bubble and shuttle sort. Okay, it is quadratic, because each time you're looking down, that's you're comparing each number to the one before it to see which is the smallest. You arrive here, that's the smallest. You've just made 4 comparisons there. Then you make 3 comparisons, 2 comparisons, and 1 comparison. So it is still quadratic. The other 2, insertion sort. This is more like how you would perhaps sort a deck of cards in your hands. You pick up the smallest and you put it into position. You pick up the first number, you put it into position. You then pick up the next one and you put it into position. You put up the next one, put it into position. Pick up the next one, put it into position. Very intuitive for a human, not so intuitive for a computer. Okay. And finally, the Quicksort. What we do is we take the group and we look at the first number and we make it a pivot. And we put anything that is smaller than the pivot above the pivot, and anything that is bigger than the pivot below the pivot. So in this case, 4 and 2 are both smaller than the pivot, and 7 and 6 are both bigger than the pivot. Now, because everything above that is smaller than they are above it, and everything that is bigger is below it, then we know that this number is in the correct position. We don't know about anything else yet, but we know that this number is in the correct position. So we can kind of lock that in place, and I'll just emphasise that with little straight lines. And when you have a number that's between 2 straight lines, then it's in the right position. You then repeat the process for each subgroup. So here we have a 4. We make that the pivot. Do this one in pink. And it's just the 2. 5 is still locked in from before. So of this subgroup, 4 is chosen just because it's the first number in the list, nothing special. 2 is smaller than it, so it goes above it. Nothing is bigger than it, so nothing goes between the 4 and the 5. And that's locked into place. Okay, now 2 also is not circled, it's not been a pivot, but because it's in a set of 1, then it's in the correct position. We do the same thing with the 7 and the 6. Okay, the 7 goes there because the 6 is smaller. So the 7 gets horizontal lines above it and below it. It's locked in position, it's in the right place, and the 6 is smaller, so it goes above it. And those are the 5 sorting algorithms.